A black hole represents a specific location where the geometry of space and time suffers a structural failure. When a star exhausts its nuclear fuel, the physical matter collapses into a gravitational void, leaving behind a violently warped spatial grid. For decades, this breakdown existed only as a mathematical prediction. The Event Horizon Telescope collaboration provided the first direct observational evidence of this geometric collapse. Physicists analyze the asymmetric ring of Sagittarius A star as a precisely mapped metric tensor. This data maps directly to Einstein's field equations, which dictate that matter tells spacetime how to curve and spacetime tells matter how to move. Within the field equation, we isolate the stress-energy tensor, T mu nu. This variable accounts for the mass and energy of the collapsing star. Interpreting the EHT image requires reconstructing the anatomy of a black hole from first principles, tracing how that mass variable forces space to break. This reconstruction begins by pushing gravitational models to their limits, starting with the 18th century flaws of Newtonian gravity. In the late 1700s, Jean Michel and Pierre-Simon Laplace proposed the existence of dark stars. This 18th century diagram illustrates a celestial body so massive that its gravitational pull drags its own light back to the surface. Because they viewed light as a stream of physical particles, they used Newtonian mechanics to calculate the mass required for the escape velocity to exceed the speed of light. If the escape velocity, the square root of 2gm/r, is greater than or equal to c, the star remains invisible. Laplace incorrectly assumed a star could maintain a constant density regardless of its total mass. The physics of this model relied on an impossible material stability. When scientists discovered that light behaves as a wave, the dark star theory was abandoned. Under Newtonian gravity, there was no known mechanism for a force to pull a massless wave. Understanding the gravity of a black hole requires shifting from mechanical forces to the physical structure of a star. A stable star is a balance between gravity pulling inward and thermal radiation pressure pushing outward. In this core diagram, the outward pressure perfectly counteracts the crush of gravity. When the nuclear fusion rate drops to zero, this internal thermostat fails. Gravity overpowers the fading thermal pressure, crushing the core instantly. Electron degeneracy pressure can halt this collapse for stars up to 1.4 times the mass of our Sun, resulting in a white dwarf. Past the Tolman-Oppenheimer-Volkoff limit of roughly 3 solar masses, even the degenerate state of neutrons cannot resist the crush. Beyond this threshold, catastrophic collapse is physically inevitable, moving the problem into general relativity. General relativity defines gravity as the geometric curvature of spacetime, dictating the paths of matter and light. In this extreme curvature, light follows the curved trajectory of space. Near the center, gravity diverts light paths so severely that it creates a central dark region, a gravitational shadow. The Schwarzschild metric provides the first exact mathematical description of this warped funnel. The Schwarzschild line element isolates the critical term, 1 minus rs/r. The variable rs is the Schwarzschild radius, the boundary where this term goes to zero. This creates a coordinate singularity, known as the event horizon, a threshold where time effectively stops relative to a distant observer. The absolute center of the black hole is the true singularity, located at r equals 0. As the radius r approaches 0, the spacetime grid's curvature extends to infinity. The event horizon acts as a strict geometric boundary, where space and time effectively trade dimensions. Real stars rotate, meaning the black holes they leave behind possess immense angular momentum. The Kerr solution is the metric that accounts for this spin. The Kerr metric integrates angular momentum through the variable a. This spin generates a new geometric feature, the ergosphere. The ergosphere touches the event horizon at the poles and bulges outward at the equator. Inside the ergosphere, spacetime itself revolves faster than the speed of light, forcing all particles to co-rotate with the black hole. Particles can extract rotational energy from this swirling metric. Through the Penrose process, a particle can steal rotational energy from the ergosphere and escape before crossing the event horizon. The Kerr metric transforms black holes from passive traps into engines capable of powering quasars and relativistic jets. The no-hair theorem states that any black hole is perfectly described by just 3 parameters: mass, spin, and charge. However, applying statistical mechanics reveals that black holes are also thermodynamic bodies. The Bekenstein-Hawking formula dictates that a black hole's entropy scales with its surface area. Because black holes have entropy, they must have a temperature and emit radiation. This radiation, Hawking radiation, causes a black hole to slowly evaporate over trillions of years. Stephen Hawking used quantum mechanics to define this radiation, triggering a massive theoretical rift. If a black hole evaporates into purely random radiation, the unique quantum information of the star that formed it appears to vanish. General relativity and quantum mechanics yield contradictory results when combined at the event horizon. Modern observational data proves that these theoretical metric deformations exist. Merging black holes send ripples through the spacetime metric, which we can now measure as gravitational waves. LIGO's strain data serves as physical proof of the metric deformations calculated by Einstein and Schwarzschild. The Event Horizon Telescope captures the exact physical boundary of the Kerr metric shadow, where light has been diverted by intense gravity. Capturing this image bridged centuries of abstract math with planetary scale engineering. While we have measured the strain and photographed the shadows, resolving the nature of the singularity remains the ultimate frontier of physics.